Okay. And then okay, so this is the first problem, and we want to find what is ultimate moment of resistance. Okay, so this is what is needed. Okay, so this problem, so I want you to first find out what is total AST. Okay, so the total area of steel, just find it out. So I'm just going to, I'm not going to write the step, I just want the number now. What is the total area of steel? What is the total area of steel?
Sir, 1106.62 mm square.
No, there is, do it again. Two numbers of 28 diameter bar and two numbers of 25.
So 2213.25 mm square.
2213.
2213.25.
So 2213. No, forget decimal places. Usually just report it in whole numbers. Okay. For no, these things, these kind of engineering things and all, area of steel and all, decimal point is not at all significant. Okay. So always have the habit of reporting it in whole numbers. Okay. So that is one thing. And then in general, whenever you have a concrete beam, capital D, if I use, it usually means the full depth of the beam. And small d always refers to the effective depth, meaning total depth minus the effective cover. As I told you, when we start to design, we'll come to, you'll be taught how to assume the cover. Okay, so till then, I'll just give you what the effective depth is itself. Okay. So AST is known. The next thing that we need to know is what is the limiting or the ultimate, what is the maximum limiting depth of the neutral axis or XU max. So this is given by a formula 0.48D if it is Fe415 steel. Okay, so depending on the grade of steel, this will change. Just like in working stress method, where Kb depends on sigma St. Here also the neutral axis depth will depend on the grade of steel, and it's given by a constant 0.48 D. Okay, so how much does this come? So D is shown in the picture, small d. Give it in whole number. Okay, whatever you get the answer for XUmax.
315.
315.
315. Okay, so now we have XUmax. Now we want to make a check, meaning that, so what do you want your beam to be? Do you want it to be balanced? Balance is not possible usually. It's very rarely that you can actually have an exact balance section. So given that, do you want it to be under reinforced or over reinforced? In general, what is preferred? Under or over?
Sir, under reinforced.
Under reinforced.
Under reinforced. You want it to be under reinforced. So assuming, so we don't know whether it is. So let's just say assuming it is, let's mean it will be under reinforced. So assuming that it will be under reinforced, you can calculate your actual neutral axis. Okay. So this is actual neutral axis. This is limiting or balanced. So the actual neutral axis you can find out by you can just remember this. This comes from compression equals to tension. Okay, this basically comes from compression equal to tension formula. So 0.87 Fy AST divided by 0.36 FCK into B. Okay. So Fy is this, FCK is 25, B is here. Okay. Yeah, everything is there. So what do you get XU? So those who want to know, please go. Somebody asked me yesterday, what's his name? I forgot the name. The student who messaged. He asked me what book should we refer. So I suggested to him this book. I think it is called as the limit state design of. I think the book name is this, or it will be something different like reinforced concrete design by limit state method. So these words will be there. I don't remember the exact title. Author is okay. So this, in my opinion, is the best book for learning problems, learning design aspects and practice. Okay. Detailing also he would have given how to draw and all those things. So this is the best book in as far as that is concerned. If you want to learn concepts and its actual behavior and all those things, the book named as I think reinforced concrete design by Devdas Menon and Unni Krishna Pillai. So this is for problems. This is the best book. For concepts and learning, this is better. Okay, so why did I talk about this now? So those who want to recollect how this 0.87 and 0.36 all come, either look at my PPT or look at Devdas Menon's book. Okay, anyway, XU, what do you get?
$253.
254 mm, sir. 254
200 how
mm.
much? 248.
54.
Others? 250 or 254 around that range?
253.
Okay, one of the 253 or 254 something. Okay, so now this is compared to XUmax, this is lesser. So is it actually under reinforced or not under reinforced? XU is just an XU max. So is this assumption correct or wrong?
So it is under
Correct only.
Under enforced, sir. Correct.
Correct only, no? Okay. 1 minute, please. One urgent call. Yes, sir. Yes, sir. Yes, sir. Oh, you cannot delete. Okay, fine. Okay. Then after that, you will be able to copy, no? Or they again, in faculty have to enter mark. Oh, okay, now anyway, mark is not there, no? It's empty only. Any faculty has. Oh, okay, okay. Just that. I think only one section has happened like that, no? Chemical or. Okay, to him alone we have to tell. Okay. Okay, sir. I'll just talk to once Maripan sir and get back to you, sir. Okay. Actually, okay. Better I will talk to the Panisalam sir in production. Then I will get back to you, sir. Okay. Okay, sir. Yeah. Sorry, pa. So yeah, this is correct. Since X is less than XMS, this assumption is correct. It is actually under reinforced. So now you can proceed to find by the formula. You can proceed to find out the moment of resistance. So M U R, okay, ultimate moment of resistance. So formula is simply compressive force, which is given by 0.36 FCKB into XU. This is the force, and the lever arm is given by D minus 0.416 XU. So here also all the numbers are available to you. FCK is known, B is known, XU you have just found out over here. This is XU. D is here, and yeah, so everything is there. Proceed and find out what you get for MUR. So since this is under reinforced, you can use either this formula, or you can also use the formula given by steel. Okay. So you can alternately you can also use 0.87 Fy AST into okay. So either of this is allowed. Anyway, use both of them and verify that you get more or less the same answer. So what do you get for this one and what do you get for this one? Just tell me. Calculate and tell me. Every single value is known. Okay, this is just a representation of how these two formula comes, just to remind you. Okay, how these formula come only, I have written this. How much do you get for, okay, MUR, how much do you get MUR? If CK is 25, B is 350, XU is 253, D is 656.
Sir, around 440 kilonewton meter, sir.
How much?
440 kilonewton meter.
440. Others do you get 440? Couple of more people give me the same answer, then so then at least I can take it as a representative sample of the class.
438.
448.
438.
438. 440, 438. Any other
Sir,
answers?
440.
438.
440.
Okay, fine. Okay, something like that. 430, 448. Something around this region. So that may depend on whether you took 254 or 253, I suppose, for XU. So okay, how about when you use this formula?
$439.
How much?
Same, sir.
39.
439. Okay, more or less the same. Okay. So anyway, so this is simple under-reinforced beam, how you analyze and get the ultimate moment of resistance. Very simple. Start with finding limiting neutral axis depth. Check whether it is under-reinforced first of all. And when you find the neutral axis, if it comes less than XU max, that means yes, it is under-reinforced. Once you verify that, you can just use one of this formula and find out what the ultimate moment of resistance is. Okay, so very simple. This problem is relatively much simple to do. Now let's move to something. Next step, we move to something which is which won't be like this. So a different problem, which I'll just draw it. And I have this is 300 and effective depth is D. D equals 655. All right. Then I also have all these are 4 numbers of 25 mm bars. Concrete grade, low grade M20 and Fe415. Same question again. Find MUR. So how do I proceed? Just follow this previous problem steps. What do you want? What do you get first? What do you find first?
Area of steel.
AST is how much? Four numbers of 25 mm dia.
1963.
1963. Okay, next. What to get? What in the previous problem? What did you find? XU or get XU max first.
XU max.
So again, this is also Fe415. So you will use 0.48B. How much is this?
$315.
314.
314. Okay. Now again the same thing. Let's assume it will be under reinforced. Assume it will be under reinforced, meaning that you can try to find XU by 0.87 FYAST divided by 0.36 FCKB. Now go ahead and proceed to find this. Okay, only thing is now your FY is again 415, and but this thing B is 300 and FCK is 20, not 25. Find out how much you get. In fact, let me make it a little more serious. Just halt for a minute. Don't do this yet. Let me halt it for a minute. Let me make a small change to it so that it appears much more serious, and then this will change a bit. Okay, so if it's Fe500, it becomes 0.460. Okay, so anyway, just slight deviation. Let's go ahead with this type of steel. If it's 0.46D, how much comes for XU?
301, sir.
Huh?
301.
301.
Yes, sir.
Okay, good. Yeah, now come back here, and Fy will be 500 now. FCK is 20 and B is how much? 300. What do you get for XU? How much is XU?
395.
395. Okay. So I simply change it for a small change this for a small reason. If it was Fe415, actually this thing came 321. Okay, the XU. So not 328. So now it's since I changed it to 500, it has gone up to 395. I just wanted to make it really over-enforced, really over-enforced. Okay. So compared to the last problem, now you find that this is actually greater than XU max, meaning that this is wrong. Okay, it's not under reinforced, it is actually over reinforced, meaning that Fst is not known. It's not equal to 0.87 F5. Okay, so this thing that you used here is actually not true. Because it's over reinforced, steel is not yielded. So therefore the stress in steel is not 0.87 Fy. It is something else which you have to find. Okay, so now you have to use an iterative process. Okay, so iteration 1. Okay, so this iteration is basically to find Fst and actual Xe. Okay, because you assumed it is under reinforced, calculated and found out it's over reinforced. So therefore this Xe is not correct, because this formula can be used only if it is under reinforced. If it is an over reinforced beam, this formula is not valid. So therefore you will have to carry out an iteration process. So basically you use something like your bisection method. Do you remember what is bisection method? Numerical technique.
Yes, sir.
Okay, so you basically, if you want to convert to a value, you find out, you get an approximate value, then calculate it, calculate the solution based on that, and if it is not same, you take the median of both of them, and then based on that you keep iterating. So like that, now you will assume that XU is nothing but the mean of these two, 301 plus 395 divided by 2. How much is this? Just find out this.
348.
Okay. So this 35 epsilon st. This is E. Yeah, how much was this? Sorry.
348 mm, sir.
348 mm. Okay. So now based on the similar triangles, you can estimate what is the strain in steel, because always strain in concrete you assume as 0.0035 in compression. So you just say that based on this you can get strain in steel is nothing but 0.0035 d by xu minus 1. Okay, so how much do you get the strain in steel? D is 655, xu is this xu which you have approximated over here, 348. How much do you get for this?
So 0.0031.
0.0031.
1.
0.0031. Okay. So others get 0.0031.
Yes, sir.
Yes.
Yes, sir.
Okay. So now we have to find the stress in steel. So for that you can use a table in SP16. Let me just show the table now. Whenever you have the strain in steel and you want to find the stress in steel for Fe415, Fe500 type of bars, then you can use this table. Let me just go through it. It's taking a while. Okay, so momentarily let me unshare. Like it's a class filter, that is it. Yeah. So let me momentarily unshare this and share something else. Okay. Now you see this table. So you have we have Fe500 bars. So you look at this. So are you seeing the PDF?
Yes, sir.
Okay. So this is SP161980. It is freely downloadable from the internet. Please download it and keep. Okay. So here Fe500 and we have strain values here and stress values over here. Okay. So because of this particular reason, we look at where we are in the strain. So we are somewhere between 0.00. So what was our strain was 0.0031. So we are somewhere close to this. Okay. So between these two, you'll have to interpolate and find out what the stress is. Okay. So so let me just note down the values for my reference, or let me just instead do share screen itself. Share screen. Okay. Now screen itself will be visible. Okay. So I have now I can just do an interpolation. Okay. So to get Fst linear interpolation you can do. Okay. So my lower bound value is 0.00277 and the corresponding stress is 413, and the upper bound is strain 0.00312 and stress 423.9. Okay, so this I can just adopt and I do. How much is it? 423.9 minus 413. 423.9 minus 413. So we want the stress, so therefore the stress stays in the numerator. 0.00312 minus 0.00277. This is the strain, and then the actual difference that we have. So what is the stress we have? 0.0031. Sorry, strain that we have 0.0031 minus 0.00277, and the lower bound the stress is 430. Okay, this is normal linear interpolation that I have done, nothing else. So if somebody is stuck up about how to actually write the interpolation, just to remind them how interpolation is carried out, I have written this. That's it. Okay, this is just linear interpolation. Okay, so this is it. Just try to find out how much they get for the stress, FST. Just simple arithmetic. How much do you get FST?
423.27.
423.
0.2. 0.3, sir. 423.3.
Okay, fine. 423.3. So FST is found. Now what you have to do is you have to find the new XU. How do you find it? Instead of 0.87 FY, you just say FST AST divided by 0.36 FCK. The FST you have found here 423.3. So use that. AST is 1963. 0.36 FCK is 20. B is 300. So how much do you get the new calculated value of XU? What do you get? The new XU? How much? How much is XU?
So 384.
385.
385.
Okay. So converting a bit slowly. It's not good for us. Okay. Iteration 2. So now you see this is 385, and what you had before was 348. Okay. So now you actually bisect it again. Iteration 2. This will be XU equals what you previously found was 385 and what you started with was 348. How much is this? So basically you are bisecting this and this way. Iteration 1 is the starting value and ending value. So you bisect that. This comes about 385, 48,
366.
360. 3, yeah.
6. 366.
366.
366. Yes, sir.
366. And then the same thing follows again. So epsilon st, again you will find 0.0035. This D is 655, 655 I think. What is D? Yeah, 655 by 366 minus 1. How much is epsilon st?
Point zero zero two
So
seven.
0.0027. Yes, sir.
0.003?
0.0027, sir.
37.
27.
0.0027,
Yes, sir.
Okay. Correct?
Yes, sir.
Okay, fine. So now going back to the table to see what we need to take. We need to take the previous two. We have to interpolate between this and this. So that becomes this equals the 413 minus 391.3. divided by 0.00277 minus 0.00226. Into 0.00277 minus 0.0027 plus 391.3. Okay. So basically, this is nothing but this. Okay, FST.
Sir, it should be 0.0027 minus 0.00226. The numerator part.
Oh, right. Okay, sorry. Correct. Thank you. Seven minus 0.00226. Thank you for that correction.
For 16.45, sir.
How much is the FST?
For 16.45, sir. For 16.45, sir.
Coming as 413.
41.
413, sir.
413 itself.
Yes, sir.
It's slightly lesser because our upper bound is itself 413.
So the strain is 0.00276, sir. So 413 only answer.
Oh, strain itself is 0.00276, sir.
Oh, yes, sir.
It's epsilon ST.
Yes, sir.
Oh, happy, yeah. Okay. So this is 276, sir.
Yes, sir.
Yes, sir.
Oh, okay. Then it will be okay. Then it will be 413 per mm square. Okay. So now new XU based on that. So ST by. I'll write the whole thing. So 413. This is FST. AST is 1963. 0.36. FCK is 20. B is 300. How much is XU?
375.
375. Okay. Now, actually, when for the sake of time, what I'm going to do is actually you will have to carry out one more iteration because still this 10 mm difference is there. Okay. Still there's a 10 mm difference and that is not actually acceptable. You have to bring it much closer. But the step is the same. Okay. So next step, what you will do is for iteration 3, what you will do is you will take 366 plus 375 by 2. Okay, and it will come much more narrower now. Then again you will find epsilon ST, again find FST, and mostly at the end of the third iteration it will converge. Okay, so for example, if you 375 plus 366 by 2 will be something like 371 or something. Okay, 370 or 371. That will be the next XU that you adopt. So mostly at the end of iteration 3, you will get something close to that number itself, and you will say it is converged, and you will use that value of FST. So I don't want to repeat the steps again. So I'll just say similarly carry out iteration 3. Similarly, carry out iteration 3. Okay. And let us assume that so initially you had 423, then it came down to 413. Let's assume that it comes down to, say XU comes something like 370 mm, and let's say that you get FST equals, or let me say first you get FST equals I'm just assuming it because I don't want to do the whole iteration and waste your time. So let me assume that FST comes 410, maybe, I don't know, you can check it out later, but for the purpose of this class, let me just assume it. And the XU then you find out as maybe 369 mm or something like that. Okay, and you will say that it is converged. And this is what you will have to use in your finding out the moment of resistance. So now to find out MUR, you will have to use these converged values of XU, and if you are using FST formula, then that value of FST. So 0.36, this formula does not change. It's 0.36 FUKB into XU into day minus 0.416 XU. Okay. So the problem is almost over. Just carry out this. Tell me what is MUR.
Sir, can we also use FST into AST, sir? The
I'm
final
coming.
formula.
First do this. I'm coming to that. Okay, so
399 kilonewton meter.
how much?
399 kilonewton meter.
398.
99, sir.
399.
Yes, sir.
399 kilonewton meter. Okay, so alternately, like somebody just said, you can alternately use instead of 0.87 Fy. So if you see the previous problem, you would have used 0.87 Fy AST into D minus 0.416 XU because it was under inversed. This is over inversed, so you have to use rather FST AST using the FST you found before. Actually, you will get a difference here because I have assumed this 369 and 410. So if this is actually a little bit wrong, then you will not get the same answer. Let me just see whether the values I took here are meaningful or not. FST AST into D minus C. So in case this does not come 399, that means the assumption that I made is a little bit bad. But anyway, you can find out the real answer by yourself. Okay, this will be a suspense to me. Let's see. How much do you get FST AST into D minus 0.416 XU? It's okay, even if it doesn't come 399, tell me what it is.
$403.
Okay, not that bad then. Okay. Others get 403.
Yes, sir.
Okay, good, thank you. So, anyway, if you actually find out the actual value, you will get not even this much difference. You'll get it even much closer. Okay, so basically, if you find the actual converged FST and XU, this will be more or less same. MUR whether you find out by this or whether you find out by this method. Okay, so I have solved two problems on singly reinforced beams. Tomorrow we'll do a problem on doubly reinforced beam. Then we'll look at some design aspects of I will look at design. This is analysis. We'll look at design based on limit state method. Okay, till now, whether working stress method or limit state method, we have not looked at design. We have not started looking at design. We've only looked at the concepts of limit state design for flexure and the analysis. Okay, finding the moment of resistance. So tomorrow we'll do doubling in first beam analysis, and then we'll move to design by limit state method. Okay, so any doubts in this procedure? Okay, so this I'll just summarize for see, the single reinforced beam, it is easy, you people understand what to do, no?
Yes, sir.
Single reinforced beam is easy enough, no? Okay, fine. So doubling reinforced beam, it's basically the same, except that when you find out XU and you notice that it is greater than the XU max, then that means it is over reinforced, and therefore 0.87 Fy is not valid. So therefore you have to find out FST and the actual value of XU. So for that you use an iterative procedure based on the bisection method, where you will actually start with XU max and the actual value of XU, bisect it and get an approximate value of XU. Then you find out the strain based on similar triangle principle. You can just remember this if you don't want to actually look at the triangle every time. You can just remember this formula. If you then based on this strain in steel, for getting the FST you have to use this table. Okay, so please download this SP16 1980. So this table needs to be used if you want to find out the stress. So based on the table you do, even though the table is for a non-linear stress strain curve, in between those points do a linear interpolation itself. It is somewhat wrong, but it's okay. It's acceptable. So use a linear interpolation and find out what the stress is. Based on the stress, find out the new value of XU. Compare this new value of XU with the XU you started with. So for example, 385 compared to 348, it is much different. So you have to iterate again. So again, do the same process with the ending and starting values of the previous iteration, and find a approximate value of XU again find out epsilon ST, again find out FST, again find out the new value of XU, see whether it is converged. If it is not converged, repeat the process. If it is converged, like say for example the new value of XU comes within 5 mm difference, if it's within 5 mm difference, you can stop the iteration. Okay, if it's more than 5 mm difference, you have to do another iteration. But in case in the exam there's a problem which you do 3 iterations and still it is not converging, it will not happen. Mostly 99% it will not happen. But in case you keep iterating for 3 iterations and still it is not converging, means you stop with the 3rd iteration and say you are using that value. Okay, so once you find out the converged value of the stress in steel and XU, use either 0.36 FCKB XU D minus 0.416 XU if you are using the concrete formula. If you are using the steel stress formula, then instead of 0.87 Fy, use FST AST into D minus 0.416 XU. Okay, so this is the process. I'll stop with this. Okay, so I'll end the meeting. Tomorrow we'll continue one more problem and then we'll go to theory part of design. Okay, I'll close the meeting. Okay, goodbye.
Thank you, sir.